In this video, we discuss learning outcome number 2 from lesson 6.2, which is all about uniform distributions. Given a continuous random variable with a uniform distribution, I'll want you to be able to graph the distribution. I'll also want you to be able to find probabilities associated with a range of values of that continuous random variable. So here are some properties of continuous probability distributions before we get into uniform distributions. First, some terminology. Continuous probability distributions describe the probability of a continuous random variable x. Now, these are associated with a probability density function, or PDF, represented by lowercase p of x. Notice that this is not capital P of x. This probability density function, lowercase p of x, does not actually tell you the probability that x has a certain value. Instead, this represents probability per change in x. Now, I don't want you to get too hung up on that detail. My point there with including it is that this p of x does not give you the exact probability. If you want probability, you're going to have to look at areas under the curve. Now, when you graph that probability density function, we call that a probability density curve, or sometimes you just call it the density curve. That's the graph of the PDF. Now, getting back to our properties. When you're talking about continuous probability distributions, probabilities, not for an x value, but for a range of x values, correspond to areas under the curve. Then, since something has to happen, since x has to take on one of its possible values in that range of values, the total area under the curve is 1, because that's saying the probability that something happens is 1. We're certain that something is going to happen. Now, in this chapter, we're going to talk about 3 types of continuous probability distributions. The first is the uniform distribution, which we'll describe in this video. Next, we'll talk about normal distributions in general, and then we'll talk about the special case of the standard normal distribution. That is the primary topic of lesson 6.1, although we talk about uniform distributions as well. Now, remember, uniform distributions are just a specific type of continuous probability distribution. We say that a continuous random variable, is uniformly distributed or has a uniform distribution if the following is true. All possible values of this continuous random variable are equally likely, or in other words, the values are spread evenly over the range of possibilities. When you look at the graph, it'll have a rectangular shape. And then since areas correspond to probabilities, probabilities can be found by finding the area under this rectangular shaped curve. So you're going to be computing areas of rectangles, which are easy to compute. The point of showing you this uniform distribution is just so that you're familiar with it, but also to help you to correspond or help you understand that correspondence and give you some examples of that correspondence between areas and probabilities. So here's an example. It says, during certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes. So everyone waits between 0 and 5 minutes. The graph would look like this. And we're going to talk about the properties of this on the next slide. So here's some properties. First, all waiting times are equally likely. Since all waiting times are equally likely, that probability density function is equal to a constant value. Now, because we're talking about a continuous random variable x, rather than a discrete random variable x, x can be any waiting time between 0 and 5 minutes. So you could be waiting 0 minutes, or 1 minute, or 2 minutes, or 3 minutes, or 4 minutes, or 5 minutes. But you could also be waiting 1.5 minutes, or 1 minute and 45 seconds. Or you could be waiting 1.234567 minutes. You can have any waiting time between 0 and 5 minutes, and there are infinitely many waiting times between 0 and 5 minutes. So that's what makes this a continuous distribution. And then lastly, In order for this area under the curve to be 1, so that that area corresponds to a probability, and a probability of 1 says that one of these waiting times is going to happen. You're going to wait sometime between 0 and 5 minutes if you are a randomly selected passenger at JFK Airport during those certain time periods. Since we need that area to be equal to 1, the height must be 1 over the range. Because if I take that 1 over the range, or 1 over 5, and I multiply it by the range, which is the maximum waiting time minus the minimum waiting time, which is 5. If I take 1 over 5 and I multiply that by 5, I get the area of 1, which is exactly what we should get, because that says the probability of waiting sometime between 0 minutes and 5 minutes is 1. It's absolutely certain for a randomly selected passenger, provided that waiting times are uniformly distributed between 0 and 5 minutes. So now let's look at a problem statement. It says, given the uniform distribution illustrated in the figure, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. In order to find the probability that someone has a waiting time of at least 2 minutes, I'm going to sketch and shade the area corresponding to x being greater than or equal to 2, because that means you're waiting 2 minutes or more than 2 minutes. So if we didn't already have this graph of the probability density function, we would create it. We would know that it's equal to a constant, because we were told that that variable is uniformly distributed between 0 and 5. And in order to find that constant, we would just take the range, take 5 minus 0, get 5, and then say, well, if the range is 5, then that height must be 1 over 5, so that the area under the curve is 1. So you graph that, and then you graph the region under the curve where x is greater than or equal to 2, because that means that you have waited 2 minutes or more than 2 minutes up to 5 minutes, because everybody waits some time between 0 and 5 minutes according to that initial assumption in our problem statement. And then remember, when you're talking about continuous probability distributions, the area under the curve represents a probability. So the shaded area here represents the probability of waiting at least 2 minutes. In order to find the area, you just multiply the length and the width. So you've got 3 times 0.2, which is 0.6. Now, in order to interpret that 0.6, you might move that decimal over twice and say, what does that mean? Well, that means that you have a 60% chance of waiting 2 minutes or more than 2 minutes when you arrive at that airport. That's what that area under the curve means.